Can everyone see the full screen?
Sir.
No, sir, your screen is not seen, sir.
So we can see your screen, sir.
Okay.
You can see your screen.
In full screen mode, sir.
Okay. So you can see in the full screen, correct?
Yes, sir.
Yes.
Okay. Can you see the slide changing also?
Yes, yes.
Yes, sir.
Okay. Perfect. One more question, probably grade 9 question. How do I go to pointer in this one? Pointer option. There you go. Okay. How do I minimize the screen? Anyway, that's fine. Okay, guys, it is fine now.
Yes, sir, it is good.
Okay, sounds good. Can you see this top screen also, or should I how do I minimize the top left one?
Sir, we are just able to see your PPT. Apart from that,
Okay.
nothing is visible. So it's
Okay.
good to go.
Okay. Perfect then. Hold on. Okay, guys, then. Okay. Good evening, everyone, and let's get started now. My today's topic for presentation, the first topic is on the advanced battery thermal management system for the fast charging protocol and the modeling part. So today is December 25, and as I think my introduction is already given, I'm an adjunct assistant professor in mechanical department, and due to my research on lithium-ion battery, I'm a cross-appointed faculty in chemical engineering department. I will go through my personal introduction. Probably it is already given, so I will skip that slide, and followed by University of Waterloo, then PhD, how to come to Waterloo, how to do the master's, PhD, or postdoctoral. By the way, I'm looking for master's or one PhD student, and I will come back to you on that later part. Electric vehicle, then we'll go for battery research, experimental setup, which I have at University of Waterloo. And by the way, I'm doing collaborative work, so I provide battery data to various institutes in India, and you guys can develop the model, validate the model, and then you can publish the paper also. We have green and intelligent automotive laboratory, which is newly developed laboratory, and followed by Thevenin model, then it's computational fluid dynamics, EV model, which I will do it in the second part, then electrochemical model, validation, and couple of papers, and along with that collaboration part. So if I go to the personal introduction, just for your information, if you type my name, Satyam Panchal, UW, you will find my profile in chemical engineering, not in mechanical engineering, because I am cross-appointed faculty in chemical engineering department. So my email ID is already here, satyam.panchal@uwaterloo.ca. So after this presentation or in future, if you have any question, feel free to send me an email, and I will be happy to answer all your questions. My research interest with the research area are provided in my website, and I'm working closely with Professor Roydon Fraser and Professor Michael Fowler, which you can see over here in mechanical as well as in the chemical engineering department. So we three work together for battery as well as the fuel cell also. I don't want to go to this slide because my introduction is already given by the professor. Then my educational background is, so I am basically from India. I did my bachelor and master's from India, and then I left India in 2005, so almost 20 years now. So I'm a Canadian citizen. I left India before 20 years, and after moving to Canada, I did my master in Waterloo, then PhD, and then postdoctoral fellow at University of Waterloo. This is my Google Scholar profile with 9,000 citations, and couple of papers are provided. And several awards are already there under my name. So you can see over here. So I was also selected in Canadian Engineering Accreditation Board called CEAB in 2013 for talk on teaching and couple of other stuff also. Then I was a recipient of Ontario Graduate Scholarship called OGS. Then I took course called uh, Engineering Thermodynamics for several years, and I'm happy to inform you guys that I got 6 times outstanding teacher award based on student recommendation for the course of Engineering Thermodynamics. In addition to that, I got a Governor General of Canada, so David Johnson Award, then James and Elias Graduate Award, Walter Metzger Award, and couple of scholarships also. So this is my something about membership as well as awards. Uh, can you please mute yourself if someone is speaking? Thank you. So, so these are my outstanding teacher award. I want to skip this slide. Uh, Probably this is something interesting for you guys. So the Gaia Lab or Green and Intelligent Automotive Laboratory, which we have in our system engineering department, and we work together. And we have several like the energy storage system testing, like the cell module as well as the pack level testing. Then we have component in loop control validation. We have emission analysis, vehicle dynamic modeling also, onboard data acquisition and dynamometer testing. And recently we started the autonomous like the driving. So this is the new research ongoing right now at University of Waterloo. And this is the setup which is there at Waterloo for cell level as well as for the module and the pack level testing. And we go all the way up to like the 1200 volts. So it's a very big system. And we received $10 million equipment from Michigan at University of Waterloo, and we have huge laboratory over there. So you can type Gaia Lab and you will find all informations about cell, module, as well as the pack level testing. My name was highlighted at WISE called Waterloo Institute of Sustainable Energy for critical lithium-ion battery. So here on the right-hand side, you can see a professor with the red puppy here, Professor Roydon Fraser. He's a teaching chair and professor in mechanical engineering department at University of Waterloo, and he's the principal investigator for green and intelligent transportation system group at University of Waterloo. You can see the another professor here called Dr. Michael Fowler. He's in chemical department, and I work closely with these two professors. So Dr. Fowler's main research area is the hydrogen fuel cell as well as the lithium-ion battery, and he is heading the green and intelligent or green and fuel cell laboratory at mechanical at chemical engineering department. A couple of reputed publications selected in applied energy, thermal energy, heat transfer, and Google Scholar Profile. Even we go every year to Society of Automotive Engineering at Detroit conference, and then we publish several papers on degradation and like the modeling also. Was also renowned reviewer for several journal, which you can see over here, and I want to skip those slides, but this is probably something interesting to you guys. So Waterloo is one of the topmost university in Canada, and last year intake was 48,000 students. So you can imagine how big is the university, and it has almost 48,000 enrollment for undergraduate as well as for the graduate, and then we have 100-acre main campus, and we have 100 plus buildings with 6 faculties. And when we started this university in 1957, there were only 74 students, and now you can imagine 40,000 students at Waterloo. I want to skip this slide, but this is something about University of Waterloo, and you can see this video later also in my presentation. Those who are in undergrad or in a master's, and if you want to come to Waterloo under my guidance or with any professor, this slide is probably very important to you guys. So first step is to get the good score in IELTS. Second one is the MSc. So if you want to come to master's program, you have to do, it is basically funded. So you get money from professor, and it is 5 courses basically, plus research and 2 to 3 journal paper, and then you are done. Second one is the MNG, is called Master of Engineering. That is not the funded program. Basically, you have to put money from your pocket, and it is typically around $15,000 to $20,000 per year. PhD is funded program, but typically it is 4 year, and you have to do the 4 grad courses, research paper, 5 journal paper minimum, and then it's 4 to 5 year course. That being said, recently we started the combined program called Masters plus PhD. In that, so you can skip your masters and start your PhD directly once you are done with first year of your masters, in which you have to do the 7 grad level courses, then research, and then minimum 5-year course. That being said, we all know Waterloo is good, but that being said, we have other good universities also. Keep in mind that all universities in Canada are according to CEAB, called Canadian Engineering Accreditation Board. And all of other top universities are University of British Columbia, that is in Vancouver, University of Toronto, and McGill University in Montreal. We have other good universities called U Alberta, University of Saskatchewan, University of Manitoba, Queen's University, that is in Kingston, then Capital University called the University of Ottawa, and McMaster, that is in Hamilton, so close to Niagara Falls. Other good universities are Carleton. These are typically used for Master of Engineering. University of Windsor, Western Ontario, Ryerson, Gulf, and the Concordia. So these are good universities in Canada. And if you want to come, feel free to send me an email, and I will be happy to give all your question answers. Then let me move to our technical part called the battery. So fundamentals of EV and battery. We all know about the EV and the battery, so I will skip a couple of slides because I want to focus mainly on my research part. So just a big idea about the battery. So what is battery? Battery is basically a number of electrical cells. So like the connected, you can see over here, either in a series or in a parallel. And basically it is electrical cells that produce direct current through the electrochemical energy into the electrical energy. And cell is typically single cell which contains anode and cathode with the 2 electrode with the oxidation reduction reaction. I want to move a couple of slides about the batteries because I have like the limited time, and I want to focus main on my research, typically on the fast charging and the thermal management system. So don't worry, I will cover this basic terminology in my second session, because the second session is like little shorter I have kept, and that way I will move. But just to give you an idea about the primary, secondary cell, then cell, module, and pack, you are already aware about that one. Couple of units I will discuss later on in my presentation. And why lithium ion battery? So this is something a story part, so I don't want to discuss much about the story. So types of batteries, cell operation, and electrochemical process, and cathode chemistry. Now just to give you an idea, battery typically contains 3 basic chemistry. One is the lithium cobalt, then the lithium phosphate, and then the lithium manganese. So here you can see the layer structure of the LiCO2 called lithium cobalt. Here you will see the lithium manganese with the crystal structure, and here you can see the olivine structure for lithium iron phosphate. Anode materials are typically graphite as well as the silicon. If you Google the company called Anivate, they have filed around 12 to 13 patents on like the silicon based anode, and they are claiming that your mobile charging is very fast when it comes to this silicon based anode. Separator materials are typically ethyl carbonate, diethyl carbonate, ethyl methyl carbonate, and dimethyl carbonate. This is typically a battery like the process which I want to skip over here because you all know how to manufacture the battery. But now if I move to the next part, that is about the problems with the gasoline. So if you look at this slide, so gas price and the environmental impact. So this is the price from so company. So in 2003 it was 52 cents per liter. Recent price even is like around $1.50. In 2011 it was like $1.23, and product, so it says that it is going to be around $2 or $2.50 in future. So your typical gasoline vehicle takes $25 to fill the gas tank, but in future you will end up paying around $125 to $150. Right now I am driving Toyota Venza. So before 20 years, I was able to fill the gas tank with around $25 to $30, but right now I am paying almost $110 to fill the gas tank. So in 20 years, you can see the increase in the gas price. So this is something about increase in the gas price. Parallelly, if you look at the right-hand side plot, so atmospheric carbon, like the ppm, so parts per million, and versus number of years. So since 1960 all the way to hold on, yeah. So 1960 all the way to recent is around like 425 parts per million. So CO2 concentration is continuously increasing since 1960. And third one, if you look at this slide, so the highest contribution from highest contribution to the greenhouse gas emission is from transportation sector, which you can see is around 32%. And second highest contribution is from power generation, which is around 20%. And so due to all these factors, gas price increase, atmospheric carbon concentration profile, and according to Environment Canada, so the CO2 concentration profile, and then the part, we need the alternative for the gasoline vehicle, and that is called the electric vehicle. The main heart of this vehicle is the battery or the battery pack. And the main problem with the battery pack is presented in this slide. If you look at this slide, this is General Motors Chevrolet Volt, which is around like the 300 batteries in the 9 module. In typical range is around 70 kilometer or 55 mile with 100% state of charge. This vehicle has this type of battery pack, and it uses this type of 20 amp hour battery. So that battery is used in this General Motors Heavy Volt. My research was on a 123 battery basically with a 20 amp hour. Now, if you look at this temperature profile at 1C, 2C, 3C, and the 4C. 1C is basically 20 ampere constant current discharge. 2C is 40 ampere constant current discharge. I can see Dr. Ashok. Is it audible? So, guys, can you hear me?
Sir, you are audible.
Okay, good. Audible. Sure. Okay. So 1C means 20 ampere constant current discharge, because this is 20 amp hour capacity. Then 2C means 40 ampere constant current discharge. 3C means 60 ampere constant current discharge, and 4C means 80 ampere constant current discharge. If you look at this 1C, so this thermocouple was pasted somewhere over here, and then temperature distribution was measured at 20 ampere. So starting from 22 all the way to around 30 degrees centigrade. When we discharge at higher current of 4C, the temperature increase from 20 degree all the way to 36 degree. If we discharge at 60 ampere constant current discharge, the temperature increases all the way from 20 to almost around 45 degree. And when we discharge the battery at 4C means like the 80 ampere constant current discharge, the temperature is around 60 degrees C. So you can imagine when we drive the vehicle with an aggressive speed of 125 kilometer per hour, and you can see, or you can imagine how much temperature is generated inside the battery pack. So during the high power discharge, battery high operating temperature above 50 degrees centigrade affect three basic parameters. Number one, battery performance, which ultimately reduces your electric vehicle range. So instead of 125 kilometers, you will get only 100 kilometers. Second, aging or degradation is one of the biggest drawback for the 50 degree. And third one, fire or explosion, which you can see in this slide. So that is why, due to all these factors, we need the robust battery thermal management system in order to regulate all the batteries within battery pack. So let's say we have 300 batteries in a battery pack in order to operate in desired temperature range. Number second, to reduce uneven temperature, voltage, and state of charge distribution, because we want to get enough voltage from all batteries, and state of charge distribution, and for safe, good performance and long battery life. And that is why we need the battery thermal management system. So my today's topic, after 20 minutes of this problem definition and personal introduction, is about the battery thermal management. For that, So this is something about HEV, PHEV. I want to skip because you all are aware about this one. Now, the focus is on the thermal characterization of the battery. So for thermal management, I designed this experimental facility at University of Waterloo, and I strongly recommend for all Indian institutes to design this type of setup for single cell or the module level testing. So like the computer for the LabVIEW program, here you can see the second computer for data acquisition means thermal, means the Kettler, means like the temperature, and other one temperature. So first one is used for the electrical parameter collection like the time, voltage, and the current. Second computer was used for the thermal parameter collection. Then here you can see the DC power supply. Then water means the water inlet to the cold plate, and water outlet from the cold plate. Karthik, I can see your message that your voice is breaking. So is this guys heavy breakdown?
No, sir, your voice is clear to us.
Okay.
Maybe Karthik may have some
Internet issue.
connectivity issue, right?
Okay. That's good then. So here you can see these two lithium-ion battery with top and bottom cold plate, which I will explain in my next slide. So here you can see these thermal management system. So two types of thermal management system were designed. First one is the air cooling, means the passive air cooling, which you can see. So if you can see my mobile in my hand, so battery was placed in a vertical position and the air was flown. So you know the air cooling, so flow over vertical flat plate was considered for this type of battery. And several thermocouples were pasted on the first surface of the battery, and on the other side of the battery, different heat flux sensors were also pasted. So here you can see the negative and the positive terminal, and on the top side here on the right hand, so left hand side is the air cooling method and right hand side is the water cooling method. Now for water cooling method, two types of cold plates were used. If you look at this bottom right picture, so here you can see this water inlet to the cold plate. So there is single inlet, and then water is flowing in the zigzag path, and then water is coming out from here. So it has only one inlet and one outlet, and it provides the uniform cooling. But I wanted more cooling near taps, means near anode and cathode. Heat generation is very high in this particular region. So if you look at my mobile, so heat generation is higher in the top area because anode and cathode are located at the top surface of the battery. So that is why during my research, I had to do a novel contribution. So I designed this cold plate called for battery thermal management system. So General Motor eliminated this cold plate and used my cold plate, which is currently used right now in General Motor Semi Volt. So it has the water inlet like this one. So here you can see water inlet means 1, 2, 3, 4, 5, 6, 7, 8, 9 inlet. Water is flowing like this one, and then water is coming out from here. So 9 outlets. So 9 inlet, 9 outlet, and this one provides more cooling in this region. So because heat generation is higher near anode and cathode during the discharge, and that is why this type of cold plate provides more cooling. So in General Motors Heavy Volt right now, they have almost 300 batteries like this one, which has one battery, one cold plate, one battery, one cold plate, one battery, one cold plate. So this type of novel contribution means the battery thermal management system was designed, and then I did several testing for thermal management system with air cooling as well as for the water cooling. So if I before I move to the next part, if you have any question, feel free to type on in the chat box, and after my presentation, so after 1 hour, I will address each and every question to you guys. So on the first surface of the battery, you can see over here on the bottom side, so 10 T-type thermocouples were pasted, and another two thermocouples were pasted near anode and cathode in order to measure the tap temperature. Then on the other surface of the battery, so on the back side, three heat flux sensors were pasted. So you can see one near anode, one near cathode, and one at the bead surface of the body, and couple of dimensions in X and Y are provided over here. And then we typically got these heat flux sensors from Omega company. This is very accurate one. It's very expensive. At that time, I paid almost $500, so almost 30,000 rupees for one heat flux sensor. So heat flux sensors and T-type thermocouples were pasted on surface of the battery, and this is something on the SolidWorks drawing. I want to eliminate this part, and then this is about the specification, which you can see. As I said, it's 20 amp hour battery, and you can see on this one type of cold plate which has one inlet and then the one outlet. Second type of cold plate has 9 inlet, which you can see over here. Water is flowing like this one, and then it provides the maximum cooling here, and then 9 outlets are over here. After that, if I go to the results and discussion part, so typical method for heat generation is the joule heating, that is the I square R, which you can, that is typically known as the irreversible heat, and it's also known as the internal resistance heating. So I into E minus V, so open circuit voltage minus the cell voltage. So if you can see my hand, so voltage measured between anode and cathode, so that is the ohmic heat. And then second part is known as the reversible heat. So IT d by dt, so change in open circuit voltage with respect to temperature is known as the reversible heat, or it is known as the change in like the open circuit voltage with respect to temperature, called the entropic change. So generally, for rough calculation, if you want to measure heat generation quickly, people eliminate the second part because this heat is very, very small as compared to the joule heating. So typical joule heating is I square R, called the internal resistance. So we measure the internal resistance of the battery and multiply by the current will give you the joule heating. And second part, basically T delta, since you are in mechanical, probably you know the entropic change and then Helmholtz and the Gibbs function. You have studied in second year of your thermodynamics also. So based on Helmholtz and the Gibbs function, we derive this heat generation equation. That is dependent on three parts. First one is state of charge of the battery, second one the current flow, and third one is the temperature. And this is the governing equation for the heat generation. That is one method. But in this one, I propose the new heat generation method, and that heat generation method is basically total heat generation from the battery is measured by stored heat, and then the Q removed from the cold plate, and then the environmental heat. So Q sensible or Q stored is basically calculated by mass of the battery multiplied by specific heat of the battery multiplied by change in temperature with respect to time. So dt by dt, where this average temperature you can see in this battery surface is calculated by summation of temperature Tij divided multiplied by area divided by the total area of the battery. And that corresponding area and thermocouple locations 1, 1, 1, 2, 2, 1 all the way to 5, 1, and corresponding areas are provided over here. I don't want to go into that mathematics right now. But the second one was the convection heat. So for air cooling, as I said, that free air was considered, so flow over vertical flat plate, which is calculated by HA delta T, and you have studied all these equations in your heat transfer, where H convective heat transfer was calculated by using Nusselt number, which is HL upon K, and that Nusselt number correlation was used, and this equation is provided, which has like the flow over vertical flat plate with a where Rayleigh number is less than 10⁹, and Rayleigh number you all know is product of Grashof and the Prandtl number, which is given by this equation. And finally, from the cold plate. So here you can see the cold plate is calculated by mass of circulating water multiplied by specific heat of the water multiplied by inlet water minus outlet water temperature. So this is something about the data analysis, and then results and distribution. As I said, if you can see my face and the mobile, so 10 thermocouples were pasted on first surface of the battery, and then average was taken. Here you can see 1C, so that is 20 ampere at 22° ambient temperature. Then 2C means 40 ampere, 3C means 60 ampere constant current discharge, and 4C means 80 ampere constant current discharge. So you can see over here at 1C, so temperature increases all the way from here to around 30°. But if you look at the higher current, so the temperature increases from 22° all the way to 50°. And these two values are always higher because tab, so the tab temperature means anode and cathode thermocouple gave the highest value of the temperature distribution. So it is concluded from this slide that depth temperature is always higher than the surface temperature at all thermocouple locations. That was about the air cooling method. If I go to the water cooling method, again, 4 types of boundary conditions were taken: 5 degree, 15 degree, 25 degree, and 35 degree. 5 degree means 5 degree inlet water temperature to the cold plate, 25 inlet temperature, 35 inlet temperature, and 45 and like the 25 and all the and 15 degree. So, and experiment was, so before I start charge discharge of the battery, the coolant was started, so that, and 2 cold plates were placed like this one. So if you can see my hand, so coolant was started so that battery surface temperature and the cold plate temperature is same. So inlet temperature is 5 degree, then 25, then 15, and then the 35 degree. So if you look at this, that is why here you can see the inlet temperature starting is 35 for 1C, 2C, 3C, and 4C. I think you have to mute yourself. Thank you. So 2C, again, starting temperature is 35 and ending temperature here you can see around 38 degree. For 4C means 35 degree temperature increases from 35 to all the way to 44. So instead of 4C with air cooling, temperature went all the way to 60 degree. Now instead of 60 degree, it is around 44. So we got around 15 degree C difference with the water cooling method. So basically from this air cooling and the water cooling, ultimate conclusion is the operating temperature has the great effect on surface temperature distribution at all thermocouple locations on the principal surface of the battery. After, similarly, instead of the single cell, I took 3 batteries in a series. So where voltage is V1 plus V2 plus V3, and then 4 cold plates were placed. So 1 battery, 1 cold plate, 1 battery, 1 cold plate, 1 battery, 1 cold plate. So 4 cold plates and 3 batteries, and all 3 batteries were connected in a series. And then same boundary conditions for air cooling as well as for water cooling experiments were repeated, and we typically pasted 18 thermocouples for this type of experiment, where I think Pankaj Patil, you have to mute yourself. Thank you. So on 3 batteries, so first battery has 3 thermocouple, second battery, so sorry, 6. So 3 batteries had like 18 thermocouples, and then the experiments were repeated: 5 degree boundary condition, 15 degree boundary condition, 25 degree boundary condition, and 35 degree boundary condition. And here you can see the temperature distribution at 1C, 2C, 3C, 4C for all types of stuff. So this is something about the pack temperature distribution, and similarly the voltage distribution. As I said earlier, 3 batteries were connected in a series where voltage is V1 plus V2 plus V3, and typical battery voltage is 3.2. So 3.2 plus 3.2 plus 3.2. So almost 11 to 12 volt. So that is why here you can see the starting voltage is higher. But if it is single battery, then you will see the starting voltage for the battery is only, sorry, I don't have that one right now. So starting voltage for the battery is only like the 3 volt. Typical voltage window when we charge discharge the battery, we take 3.6 to all the way to 2.8 for the battery. Anyway, so this is the voltage distribution for 5 degree, then 15 degree, then 25 degree, and then the 35 degree boundary condition. And again, 1C, 2C, 3C, and 4C discharge. So you can see over here at 1C discharge, you will see little flat curve, then the 2C, 3C, and the 4C. So if you discharge the battery at higher current, you will see the drop in the voltage. So voltage window, as I said earlier, is between 11 to 7 volt because all cells are connected in a series, and the discharge capacity of the pack decreases with increase in the discharge rate. So starting from 20 ampere means 1C all the way to 40 ampere means the 4C, and decrease in operating temperature starting from 35 all the way to 5 degrees centigrade. I did not go below 5 degrees centigrade because then we had like water bubble issues, and we had to add like the glycol, so water glycol mixture, but I did not do any 0 degree or negative temperature experiment. But we have a facility for thermal chamber inside the laboratory. We have refrigeration unit also, and we did those experiments also. After that, here you can see the surface temperature distribution at again 20 ampere, 40 ampere, 60 ampere, and 80 ampere constant current discharge for air cooling as well as the water cooling. So for air cooling, as I said, ambient temperature was considered 22 degree and flow over a vertical flat plate. And for water cooling, 4 different temperatures, 5, 15, 25, 35 degree were considered. So if you look at this plot, or probably at the bottom table, so passive means the ambient air cooling 22 degree. Here you can see as current increases from 20 ampere to 40 ampere, temperature distribution increases on all thermocouple locations. But if you look at the 5 degree, so at 1C, max temperature is 10 degree, and at 4C, max temperature is 18 degree. If you increase the boundary condition, and at 4C, the temperature is 42.3 degree C. So it is basically concluded that increase in C rate increases the surface temperature distribution or temperature distribution and the heat generation from the battery, and increase in the boundary condition increases the surface temperature. Now, similarly, as I said earlier, is on other surface of the battery, we pasted heat flux sensor which measures heat flux directly in watt per meter square, which is used for heat generation calculation. So average heat flux in watt per meter square for air cooling method is 22 degree. At 1C, 2C, 3C, and 4C is provided over here. And similarly for water cooling method for 5, 15, 25, and 35 degree is provided over here. At 1C, 2C, 3C, and sorry, 1, 2, 3 locations, and at 1C, 2C, 3C, and the 4C. And corresponding plots are provided over here. If you guys are working on any modeling or anything, and if you need this data, raw data, I will be happy to provide all data for your research or for your PhD, masters, or for your further work. After that, as I mentioned earlier, heat generation method was used to calculate heat generation rate per second, means joule per second, that is in watt. This is the transient heat generation from a battery at different C rates. So 1C, 2C, sorry, 3C, and sorry, 4C. So 2C 5 degree, 15 degree, 25, and 35 is provided over here. And same way, 4C, 5, 15, 25, and 35 degree centigrade is provided over here. So here you can see the initial drop of voltage, and that I will explain in my next slide. So this is the heat generation and at 2C degree and corresponding voltage profile. And here you can see the 4C and corresponding voltage profile at the bottom side. And again, heat generation was based for air cooling as well as for the water cooling, and for 22 degree, and water cooling for 5, 15, 25, and 35 are provided over here at different C rate of 1C, 2C, 3C, 4C. And it is concluded again that for water cooling, the highest heat generation was at 5 degree and 4C, and lower heat generation was at 1C and 35 degree C. Again, so what is the purpose of whole study? So the purpose of whole study is to get the effect of discharge rate, means the C rate, effect of C rate, and operating temperature, means the boundary conditions. Let's say if you put this battery or this General Motors Chevrolet Volt in India, where we have almost 45 degrees C temperature, and if you put the same vehicle in Canada, so right now in Alberta, where we have like, let's say, minus 35 degrees C temperature. So minus 35 all the way to 35 degrees C, what is the temperature distribution on the surface of the battery? So the effect of C rate is provided over here, and corresponding for air cooling as well as for the water cooling for 22 degree, and then the amp hour discharge capacity. As I said earlier, this battery has 20 amp hour capacity. So 1C discharge means you will get close to 20 amp hour. But if you go at 2C, 3C, and 4C discharge, you will not get 20 amp hour. You will get around 18 ampere hour. So you can see over here. So even at the 4C for air cooling, you are getting 18 amp hour. So same way, but if it is like the cold temperature, you will get only 15 amp hour capacity. And if you put the vehicle closer to 25-degree, you will get around 18 point something amp hour. So I just want to highlight here that if you drive aggressively, or if you discharge the battery with very high current, you will get lower capacity. And if you drive the vehicle in very cold environment, so right now, let's say I have another car that is Tesla motor. Probably you are aware about Tesla motor. They are using cylindrical battery. So if I go from I'm in Waterloo, and Toronto airport is, let's say, 100 kilometer. So if I drive 100 plus 100, so 200 kilometer, then that's it. I don't get more range. So Tesla North American car has around 450 mile, but I'm not getting 400. And I can see Dr. Kishore, my voice is not audible. Guys, can you hear me?
Yes, sir, you are audible.
Sounds good then. Okay. So if I have a Tesla, uh, like I'm driving, so I'm getting, instead of 400 kilometer, I'm getting only 300 kilometer. Plus, those electrical accessories like wiper, radio, heater, or air condition. And that is why you are not able to get the enough range. So the range anxiety is one of the biggest problem when it comes to this lithium-ion battery. So these are the problems we are facing right now when it comes to electric vehicle battery. After that, we took IR images of the battery. So here you can see the IR image of the setup, and we use the FLIR thermocam. So this is by the very expensive camera, and we had $100,000 camera, so almost 60 lakh rupees camera. And I got it from Building Fire Laboratory. So we have a separate laboratory headed by Professor Elizabeth Wakeman, and we have big setup. And her research area is only the fire, so building fire, furniture fire, wood fire, car fire. So she's working only on this building fire stuff. So fire dynamics laboratory basically. And so I use that camera in order to get the IR images of the battery, in order to get the temperature distribution. So here you can see during the discharge of the battery, so the current start flowing, and then so this is beginning of discharge, this is the middle of the discharge, and here you can see complete red figure, that is at the end of the discharge, with two different types of battery. So here you can see smaller battery, 16 amp hour, and here 20 amp hour battery. So the whole purpose of this study is to find the lowest spread in temperature, and that is observed at the beginning as compared to the middle and end of the discharge. Second, if you look at this brightest white part in all images, is the temperature. So where the highest temperature and corresponding highest heat flux in watt per meter square is expected. And third one, it is expected because Joule heating, that is I square R, is the dominating effect, and that is why here you can see this higher one. This type of study is basically helpful in assessing thermal behavior of the battery. So instead of doing those expensive experiments, if you put this gun in your battery, you can quickly get those images, and you can use those thermal behavior to point out trouble area, and you can provide insight into improvement of the design. And that is why recently, so instead of anode and cathode on the same side, because heat generation is higher near tap, the new battery is like this one, which has anode and cathode in the opposite direction. So anode is on the left hand side and cathode is on the right hand side, where you can see, where you will see the heat generation in the uniform side. After that, thermal images were taken at different C rates of the 4C as well as the 2C and the 3C. And here you can see the blue image at the beginning of the discharge, little yellow at the middle of the discharge, and then this is the end of the discharge. Again, I have several images, around 2000 images. So if you are working in thermal area, and if you need any of these images or any data, feel free to contact me, and I will be happy to provide all data from University of Waterloo. After that, another part for thermal characterization or thermal management is the thermal conductivity measurement. For that, probably it is also a new topic for you. Open the battery, means battery dissection. So first part is the cutting the battery. Basically, we cut the battery outer edge, and then opening the battery. Here you can see the opening of the top layer, then cutting the electrode. Here you can see the anode and cathode cutting, and after that opening and counting layers. So here you can see cathode, anode, as well as the white color one is the separator. So black color one is the cathode, white color one is the separator here, and here you can see the golden color one is basically that is the anode. Here anode, cathode, separator, anode, cathode, separator. And when we did the battery dissection, it's, I can see Praveen Kale is requesting to annotate. Okay, so we found that there are 48 pairs of anode and cathode, means 24 anode and 24 cathode. And yes, I think I saw one of the question. Yes, we did it in the uh, so here you can see this battery meant. So later on, what we did is we took our own batteries and I made my 1 inch by 1 inch battery with different layers of cathode. So 7 layers, then 13 layers, then 19 layers, and then 25 layers of cathode. And same way for the anode. And then I measured the thermal conductivity of this battery and thermal resistance in order to helpful or for the like the for our other like modeling parameter. After that, uh, not able to move the slide.
Please enter spacebar or enter.
No, enter in the space bar and no. I cannot move the slide. Tab key to select color. Okay, good now. Okay. And then thermal conductivity setup and thermal resistance measurement. So different layers. So the top one is the aluminum is the contact resistance, then the pouch resistance, and then the layer resistance, and then thermal resistance in Kelvin per watt was measured for number of units. So like the 7 layer, then the 13 layer, and then 19 layer and 25 layer were measured with the slope is provided over here. And then here you can see these uh, thermal resistance were measured, and after that, based on that IR images which I explained earlier, that one line near anode, cathode, and then separator means the middle line. This change in temperature with respect to time and dt by dy were measured, and corresponding linear fit equations are also provided. So I did enough investigation on this battery and then measured those dt by dt. And again, thermal conductivity setup and thermal resistance. I think Varsa, your co-host, I will come back to you later on. Let me finish my presentation first. So here you can see this thermal conductivity setup, and here you can see the RTD means resistance part. So here you can see those load distribution thermocouples, and 1 inch by 1 inch sample was placed over here, and at different layers, as I said, 7, 13, 19, and 25 layers at different load pressure, thermal resistance was measured, which you can see over here. So this type of data is helpful to thermal modeler also. And then, as I said, thermal conductivity was measured for 7 layer, 13 layer, 19, and then 25 layer with a linear fit equation. So thermal resistance in watt per meter Kelvin and thermal conductivity for different layers of anode and the cathode were presented. And this type of study, we got big project from one of the battery manufacturing company, and they wanted to measure this thermal conductivity. So we did enough investigation on all types of the battery. That being said, uncertainty analysis, I just want to say that we did the uncertainty analysis in the temperature distribution, average temperature, sensible heat, watt, then mass flow rate, coolant, like the cooling medium, environment heat, and heat flux sensors, and all those ones. I don't want to go into detail right now, but we use the Moffat method for uncertainty analysis. This is something on the battery thermal management side for the experimenter. And then the important part is the validation, means the model development. So first one, is the CFD model called the computational fluid dynamics for the water flowing inside the cold plate, called the Reynolds average Navier-Stokes equation, called the Rance model, and those governing equations. So basically, water flow based on the Reynolds number, we found that the water flow inside the cold plate is the turbulent, and it is modeled by using this Rance approach, where governing equations are provided over here, and then here you can see the delta is the gradient factor, v is the average velocity in the meter per second, speed in meter per second, then rho is the density, and PR is the Prandtl number, P is the pressure, then PR is the Prandtl number, and R is the Reynolds number. And turbulent kinetic energy and heat dissipation equations are provided over here, where C1, C2, C3 are typically, here you can see C1, C2, and C3 are the constants, and sigma K and epsilon are turbulent, and Prandtl number for K and heat generation, and those Ym represents contribution of fluctuating dilation in the turbulent, and SK and SE are the user-defined source term. I don't want to go into software and governing equations, but these are the typical governing equations used for CFD, means the CFD, computational fluid dynamics modeling. And then here you can see over here, so cold water enters from here, and then hot water is coming out, and due to contact with the battery, it immediately gets heated, and here you can see the like the distribution of the flow, and then we measure the velocity distribution, temperature, and the pressure distribution for this particular battery. After that, here, okay, as I said earlier, so again, the next part is probably the meshing part. So here you can see those meshing, and I don't want to go into that mesh, but it's a tetrahedral mesh. Then those governing equations, and meshing was also done in the same software. And by the way, you can use ANSYS as well as the COMSOL. And for this particular stuff, we use the COMSOL software. And here you can see the temperature distribution. So inlet, and then it immediately gets heated because the heat generation from the battery, and here it is coming out. So cold water enters and hot water is coming out from this. So again, a different flow pattern 1, then flow pattern 2, then flow pattern 3, and then the flow pattern 4 are provided over here. Again, later after Rance model, means after computational fluid dynamics model, we did the optimization study. So let's say instead of 1 channel, or so let's say instead of 9 channel, if you have lower channel, so what is the effect on the flow? So optimization study has like the 4, 6, 8, and then the 10. So here you can see the number of channels. So here 4, 6, 8, and then this one, and then pack distribution was done. So same study, but we modified the geometry, and we extended this project for the pack level stuff. So you can see over here 3C discharge, then 4C discharge, then corresponding temperature distribution, and here at the bottom side the at different flow rates. So we did the enough optimization study with the flow rate as well as the mass flow rate, and then this coolant channel part also. Here you can see the 4, 6, 8, and 10 channels. So if we have, like, let's say only 4 cooling, then what is the distribution on the velocity as well as the temperature? 6 cooling channels you can see over here, then 8 cooling channels, and then the 10 cooling channels. So here the 4 cooling channel, then here you can see the 6 cooling channel, here you can see the 8 cooling channel, and here you can see the 10 cooling channel. So this type of optimization study can also be done with different types of batteries also. So this battery has this anode cathode on the same, means on the top surface of the battery, but you can have on the other surface of the battery also. And so the first model is the CFD model. Second model is the electrochemical model. So now for electrochemical model, just to give you an idea, it has like the, if you open the battery, as I showed in the battery dissection, means opening the battery, it has negative electrode, positive electrode, and then the white color separator sheet, and positive current collector, then negative current collector. So during discharge, current flow from positive to the negative, and then electron travel from lithium ion travel from a separator sheet from negative to positive, and electron travel from negative to the positive electrode. And then during discharge process, lithium diffuses to the surface of the negative electrode particle and undergoes electrochemical reaction. This reaction typically releases electron and transfer lithium to electrolyte phase, and lithium diffuses and conduct through electrolyte solution to the positive electrode, where similar reaction transfer lithium to the positive solid phase. So the lithium is stored basically in the positive electrode particle until cell is at later stage is recharged. For that type of electrochemical model, we consider this one. So length of negative electrode, length of positive electrode, and then the length of separator. So the total length is considered as Ln plus Ls plus Lp, means negative, positive, and the separator. And here you can see the particle radius, means the time for the stop. Different governing equations used for electrochemical modeling are like the charge conservation in solid phase, basically governed by the energy dissipation, which is given by this equation, and boundary conditions are at x is equal to negative current, and then the Ln plus Ls, means negative plus separator, are provided over here, and where J is the transfer current resulting from lithium insertion and de-insertion at electrode electrolyte interface, which consumes or generates the species, and effective conductivity is given by the sigma effective. Then charge conservation in electrolyte phase, that is the energy conservation, is given by this equation, where x is equal to 0 boundary conditions and x is equal to L boundary conditions are provided over here, where K effective is the effective diffusion conductivity, which is given by K into epsilon beta, where beta is the Brugman porosity exponent, and C is the concentration of lithium in the electrolyte phase. Then third governing equation is lithium conservation in solid phase, that is typically phase transition and ion transport, and that is governed by Fick's second law in spherical coordinate, which I explained earlier. So in the spherical coordinate, like in this direction, which is given by this equation, where at radius r is equal to 0 and radius r is equal to rs, those boundary conditions are provided. So where Cs is the lithium concentration of lithium in solid phase, and C is the concentration of lithium in the electrolyte phase. ds is the mass diffusion coefficient, r is the radial coordinate along with the active material, and rs is the radius. And same way, electrolyte phase are provided over here, and x is equal to 0 and at x is equal to L, boundary conditions are provided, where T plus 0 is the transfer number of lithium, and epsilon S is the volume fraction for solid particle, and epsilon F is the volume fraction for filler material. And electrochemical kinetics, so basically Butler-Volmer equation is provided by this equation, and efficiency is the 5s minus E minus U is the where 5s and E are the phase potential in solid and electrolyte phase, and U is the thermodynamic open circuit potential, and energy equation is given by this equation, where Q dot is finally
Sorry for the disturbance, sir. Excuse me, sir.
Yeah.
Excuse me, sir. Sorry for the disturbance. So are you telling all this equation from the PPT?
Yes.
But PPT is not changing. Experimental result IR image only it is there.
Oh, so
Yes, sir.
No, sir, it is going on, sir. It is going well.
Okay. Are you able to see the slide change?
Yes, sir.
Oh, we
Yes,
are
sir,
it is viewing clearly.
Okay.
It's now electrochemical thermal model equation.
And parameters?
Right, sir.
Are you able to see the table?
Sir. One
this
maybe
table,
might be
right
I'm
table.
only seeing IR image, experimental result IR image PPT. I log out and come in, sir. Thank you, sir. Thank you, sir.
Yeah, probably your screen is frozen. So I think I'm going in correct direction, right?
Electrochemical thermal.
Slides are moving, sir.
Yes, sir. Yes, sir.
Yes, sir. Sorry.
Sir, everything fine.
Okay, that's good. Because I'm about to finish my presentation. This is my last model. Okay, so energy equation is provided by this one, where 5 plus and minus are phase potential for positive and negative, and U is the thermodynamic open circuit potential. Well, if you want to model electrochemical part in console, then you need almost 70 to 80 parameters. But based on my based on my experience, typical parameters which play big role in electrochemical modeling are the length of positive electrode, negative electrode, and then the length of separator. So these values are very important, and I measured those values. Number second, those particle radius also play big role for, so the particle radius for positive as well as negative electrode in are provided over here, and maximum solid lithium concentration for positive electrode and negative electrode. So these are the typical parameter, and reference diffusivity for positive and negative electrode, conductivity for positive negative electrode, and then Faraday's constant and couple of other parameters. I don't want to go into detail. Go to my one of the paper on electrochemical modeling, and you will find detailed modeling parameters, governing equations, boundary conditions, meshing, everything for those one. And final part is about the validation. So when it comes to electrochemical model validation, so if you look at the bottom side, so voltage, as I said, so typical voltage window is between like the 3.6 to 2.0, and corresponding voltage profile temperature distribution is provided over here at 1C, 2C, 3C, and 4C, and corresponding voltage profile at 1C, 2C, 3C, 4C. So the 4C is over here. So if you discharge the battery at from 4C to the 1C to 4C, you will see this one, and corresponding temperature distribution and the model validation you can see over here. Some discrepancies are observed at the higher side, means the higher temperatures or higher C rate, and later on we refined those parameters, and then we published the second paper on electrochemical modeling. So the first model has little discrepancy for higher C rate. Similarly, what we did is for air cooling as well as for the water cooling, we got a couple of beautiful cosmetic images which you can see over here. So like at the 1C, 2C, 3C, 4C for air cooling as well as for the water cooling, like the 5 degree, 15 degree, 25 degree, and 35 degree boundary conditions. So you can see over here for the lumped model and then the lithium ion battery. So as I say, and by the way, both tabs, so positive and negative tabs, were included in the model because the tab temperature play big role in electrochemical modeling. So I have seen a couple of models or a couple of people publish the paper, but they don't consider the tab temperature or tab. So tabs play big role for electrochemical modeling also. I think that is probably the last part of my presentation, and a lot of interesting papers. If you type my name, you will find around 120 or 125 journal paper on on lithium-ion battery, and I spent almost 17 years on this particular research, including my masters all the way to postdoc. And then after I don't want to disclose those names, but I've filed 5 patents right now. One on the battery state of power, second one battery open circuit voltage, third one on the battery aging, means this degradation, then fourth one is on the tear down of the battery, and fifth patent is on the temperature stuff. So I filed the 5 patent, and they are with the US patent office almost 20 months now. Probably I will get answer soon. Thank you very much for your attention, and I will be happy to give question answers. I have added this particular images because left hand side part I have covered today in my first session, and second session is very important those who are interested in electric vehicle. So I did enough investigation on electric vehicle, and that is particularly Ford Escape one, and I will explain in my second half of the session for this particular part. So I think
Sir,
thank you so much for your attention, and I will be happy to give question answers.
Thank you so much, sir, for
good evening.
wonderful knowledge sharing, sir.
Sorry.
Sir,
Yeah.
good evening, sir. Can I ask one question regarding this matter?
Hello?
Yeah.
Hello, sir. Do you hear me?
Yes.
Hello.
I can. Yeah. I can hear you.
You have shown electrochemical batteries that is setups around the temperature 30 degrees. You said no.
You are talking
Hello?
about experimental result or the modeling side?
Yeah, results around that results.
Hold on. You're talking about this one.
The
air
battery
cooling water.
around your battery behavior is around temperature is 30 degrees. Something you have said on it.
Hmm.
Yes or no, sir?
So temperature is going all the way from 22 degree all the way to.
No. One question. Just regarding that temperature, I am asking. That is okay in Waterloo. In America, it is okay. The temperature is around 30 degrees.
Oh yeah,
But
okay.
in India, some of the places where the temperature is very high, around 50 degrees centigrade.
Yeah,
Is
yeah.
there it is a suitable this kind of battery this battery setup is suitable in this temperatures?
Yes, yes. So that is why we do the battery testing. So if you can see this battery, or let's say lithium ion, we do the battery testing starting all the way from.
No. If temperature will be rises, means fire hazards. There is a probability of a fire ignitions will be there. Possibilities of a fire ignitions. So what is the remedies are there for protecting this battery?
That is very good question. So you are diverting me on very hot topic called the thermal runaway. Good topic.
Yeah.
Yeah. So if something happens in the vehicle, so we typically put the sensor 5 minutes, and then all cells goes into thermal runaway where temperature goes very high. So if it triggers above 50, so typically when we design the battery, we put the thermal management system. So optimum range is 10 to 38 degrees. So above 38 degree, we put the cooling medium on the batteries, which cool down all the batteries. And below 10 degrees C, we need the heating system. Otherwise, you will not get the range. So that is why we need the heating and the cooling on periphery of the battery pack.
Mm-hmm. Right.
Getting or
Thank you, sir. Thank you.
okay.
Yeah, Dr. Panchal, I have a small question.
Sure.
Actually, in your presentation, you talked something about uncertainty analysis.
Yeah.
Sir, would you please tell us what is the significance of this analysis?
So typically when you do any experiment, we always go for uncertainty analysis. Okay, and that is required for your analysis. So this is the typical. So temperature distribution is around 2%. So 5 degree all the way to 47 degrees centigrade. Then average surface temperature. When you do any experiment, then you have to do this uncertainty analysis.
Okay.
Okay, and typically we measure relative and absolute uncertainty in percentage.
Yeah, sir. Thank you so much for the wonderful knowledge sharing, sir. Thank you so much, sir.
Sure. Let me go to the chat box, because there are several questions. Yeah, I can see now. Okay, I think I have to go all the way to up. Okay, by the way, my email ID is provided over here, and please send all questions during presentation. Okay, this is my website, so the link is there. By the way, before we go to this chat box, I am looking for either 2 master student or 1 PhD student, and the topic is on the battery thermal runaway. So if you put the nail on the battery, so since you guys are in mechanical or electrical, so if you put the nail penetration on the battery, and those gases are coming out of the battery, like the CO, CO2, C2H4, C3H6, C3H8, particulate matter 1 to particulate matter 4. That type of project is there right now. I do have money, means the funding from the company, and so either 2 masters or 1 PhD student, and this is something on the thermal runaway of the battery. And by the way, that is very hot topic right now in the industry. Thermal runaway of the battery cell as well as the pack is very hot right now. So if you are interested, send me an email, and I will look at your profile, and then I will let you know, guys. So that is first one. Now let us go one by one. You are audible. Good evening, sir. Good evening, Vaisali Patel, Dr. Rao, then Maulik.
Sir, should I read the question for you?
I think that is better.
Okay, fine. So there is one question from Sharat Chandra. He's asking which parameter is critical for designing an effective battery thermal management system.
So first one is the cooling medium, second one is the flow rate, third one is the type of the battery, and then couple of other parameters including the like the selection of the coolant. So either water glycol or refrigeration or types of the refrigerant parameter. Like typically people use the refrigerant R134 also. So again, several parameters are considered when you design the battery thermal management system. Yeah.
Again, the question from the same participant. What is the main advantage of liquid cooling in battery thermal management system?
So liquid cooling provide more cooling as compared to the air cooling, but again, see, everyone has pros and cons. So water cooling is more effective as compared to air cooling. Number second, water cooling provides more cooling, and third one, it provides uniform cooling also. Number fourth one, but when it comes to the weight, it's very high weight. So this is only one drawback when it comes to the water cooling. Okay, yeah. By the way, Tesla is the only one using the air cooling, and remaining companies, General Motor, Ford Motor, any other, they are using the water cooling method. Okay.
Sir, we have one more question from Vaijayanti Deshpande. She is asking whether positioning of battery, vertical or horizontal, affect the cooling.
Yes, but typically when we do the battery, so this type of prismatic or battery, if we do, we put the cooling channel at the bottom side. So all coolant channels are at the bottom side of the battery, and that is typical design of the battery pack. So we almost all OEMs are putting coolant channel at the bottom of the cell.
Sir, we are having one more question from Dr. Pradeep. He is asking, liquid cooling systems are presently implemented in any EV.
Yeah.
So he is asking whether it is implemented in any EV.
Yeah. So Google is GM SaviVolt. General Motors SaviVolt is using the water cooling one. I don't know about Indian stuff, but in North America, yes.
There is one more question from Venkatesh. He's asking, is there weight variation for air cooling and water cooling? And how does it affect the performance? And also, how does it affect the battery cooling?
So Venkatesh again, so you are comparing apple versus orange. So basically when it comes to air cooling, they are using this type of like the cylindrical battery, where they put like the batteries in, I don't know how do I explain. So they put batteries like this one, and then they provide the uniform flow, like the Tesla motor. But if you talk about the General Motor or Ford Motor, they are not using cylindrical battery. They are using this type of battery where they need the water cooling stuff with the coolant channels at the bottom sides. Where lithium plating, probably this is new word for you, but lithium plating is one of the biggest concern for this type of battery versus Tesla, and I think that is why Tesla is one of the successful when it comes to electric vehicles. Even phase change material is also one of the coolant medium, but I don't think people are using that one right now.
Sir, there is one more question. How do different automobiles choose the C rating, and what way the affect the performance of the vehicle?
So C rate basically defines based on the drive cycle. So when we design the electric vehicle, we consider the NEDC drive cycle. NEDC is called the New European Driving Cycle, or you can consider WLTC, like Worldwide Light Duty Test Procedure. So that typical drive cycle contains everything like the city driving, highway driving, and the highest speed and the lowest speed. So based on that drive cycle, we design the battery. So C rate is basically defined based on that particular drive cycle. And typical all OEMs, when they design battery, they typically do the same one. I think that was the first question. Second part, I missed one. Can you repeat the question one more time?
And how it affect the performance?
Oh yeah, so it basically so the C rate affects C rate play big role on performance of the battery. Again, a simple example: if you drive vehicle aggressively, so let's say with 125 kilometer per hour, you draw the maximum current from the battery, from battery pack, which provides maximum heat generation. So again, C rate provides, or C rate is the big C rate play big role on performance of the battery.
Sir, I think the questions are over. We
Mhm.
can have a short break and then we can
Sure.
resume for your next session.
Sounds good. Perfect. So I have like around, it's 7:20 right now. So we have like the 10-minute break, guys.
Okay, sure, sir. We'll meet at 7:30.
7:30. Okay. Thank you.
Hello participants, we are going to send the feedback link after second session. Please note.
And I'm available also. So if you have any question during this time, feel free to chat with me in this.
Hello,
Yeah.
myself Dr. Dipesh Pardesi from Sanjivani College of Engineering, Kopargaon, Maharashtra. Sir, you
Yeah.
have mentioned one thing, you will require some assistant who have completed the degree for the master's as well as for the PhD.
Yeah.
So,
Yeah.
what is your requirements? Means which thing you will want in that candidate?
Well, so it's experiment plus modeling. So and by the way, we already bought accelerator rate calorimeter with around $60,000 to $70,000 from government grant, and we have that ARC calorimeter. We have batteries, and so we need a guy who is comfortable with experiments and plus modeling. So when it comes to modeling, he should be aware. He or she should be aware about console or MATLAB. So these type of softwares. It's a
Uh,
simple one. It's like
okay,
the
it's a
thermal
console
runaway.
MATLAB because already I have implemented a MATLAB and ANSYS for such a research internships.
ANSYS is fine. People do the ANSYS, but when typically it comes to the gas flow like CO, CO2, C2H4, C3H6, C3H8, particulate matter 1 to 4. So those gas analysis, typically people use this type of software like the ANSYS console, or when it comes to 3D part for the pack level, it's different, but for the cell level, people use this one.
Okay. Thank you,
Okay.
sir, for
And
this
even apart
guideline
from
because
these,
we will want to implement in our students also.
oh, okay. And even if you need any data, feel free to contact me. I'm already providing this data to various IITs like IIT Bombay, IIT Delhi, and you can use my experimental data. But only requirement is when you write the paper, uh, you and your student, and same way myself and other two professors at the end of the manuscript. And that way
Yes,
it is
yes,
called collaborative
definitely,
work.
sir. Definitely, whenever we are writing any paper and we are utilizing any data, so in
Sure,
references, we are going to get add your reference, and
sure.
even required, we can writing the mail also to give the permission to use your data for the reference purposes.
Sure, sure. Okay, and I'm very positive. So instead of keeping my data in hard disk, it is better if I provide to you guys.
Yes, sir. It is definitely because of that, new generation will again going to get know and they can use their brain on that.
Yeah, yeah.
Yes,
And
sir.
I'm very
Thank you
positive.
all.
Even if you talk about Dr. Roydon Fraser and Dr. Fowler, they might not give you answer because they are very busy professors, but
Yes,
they are
sir.
very helpful in nature.
Yes, sir.
Okay.
So definitely I will come in contact with you, sir. So already I have note down your email ID
Sure.
and I will I expect that you will share your data with us. So on which the students will work out on that and definitely they will find out some solution in MATLAB or ANSYS.
So my understanding says that you are working in battery area, right?
I am working in few multiple areas, but when I have starting my students, so from first year itself, I am developing them into a particular domain. So
Okay.
I have, for next 4 years, they have to work in particular domain. And if
Mhm.
I have given them the battery management, so I am providing them the details of the some renowned person from the market. And from
Mhm.
first year, they have to follow them. and they have to develop themselves in the same region or same domain.
Are you talking about cylindrical battery or this type of big, like the pouch battery?
No, this is lithium battery, sir.
No, I'm talking about the construction. Is it like the cylindrical battery or the big battery?
No, at this moment it is cylindrical battery.
Okay, cylindrical one. Okay.
But I will want to develop my student in this region, and that's why I'm attended this FDP.
Sure.
Okay, thank you, sir, for your definitely I will come in touch with you.
Let me take 5-minute break now.
Yes, sir. Okay, thank you.
Sir,
Yeah. Hi.
Professor, myself, Dr. S.J. from Chennai. Actually, I am new to this electrical vehicle. Okay, if a research scholar is coming towards me, sir, I want to do research work in electrical vehicles. In which area I can provide? Sir?
Okay, so then attend my second session. Second session is very helpful, very informative, and very advanced research. And that is typically on the EV. Okay, it's not on the battery; it's on the EV.
Okay, sir. Okay, sir.
So,
thank you, sir. Thank you.
Okay. Let me go to washroom, and I will be back in 2 minutes.
पकडत पकडत त्याला चालणं शिकवलं. याच्यासोबत बाबांची घरी येईपर्यंत तासन तास वाट पाहिली. आपल्या पहिल्या बिझनेसची
काय झालं लगेच असं आमचं काय असं माझं काय झालं
Hello, sir.
You guys can see my screen now, correct?
Yes, sir. Perfect, sir. Perfect.
One more question. Good slides. You can see slide change also, correct?
Yeah, yeah.
Okay,
Perfectly all right.
perfect. Okay, and then okay, it's 7:32. Can we start now, or should we wait for another 2-3 minutes?
So we are scheduled at 7:30, so we can start.
Okay. Okay, so good evening again, and welcome to the second session of this ATAL part. So introduction to electric vehicle and advanced battery modeling part. And this second session is going to be focused more on electric vehicle instead of the battery. So again, I don't want to go into my personal introduction because you all are aware about me now. So if you look at these two parts, so this is the Ford Escape. So first Canadian electric vehicle at that time, I think in 2010. Yeah, so we started this research in 2010. So this is the company called REV. So if you look quickly over here, so it's a rapid electric vehicle. So that company is in Vancouver, and so they took actually, or we got this Ford Escape electric vehicle, and for our research purpose. And this company called REV, that is in Vancouver, British Columbia, they convert this vehicle into electric vehicle. So basically they took out the engine and everything, and then they put this battery pack, and then we got this vehicle for our research purpose. So this this project basically supported by Transport Canada, that is government sector, and where we were 3 partners in that one, and I will explain in detail about that part. Again, in this I will skip my personal introduction because you are aware about me, Waterloo, MS PhD, electric vehicle, and yeah, EV part I will cover, then battery research, then experimental setup, then again Thevenin model, electric vehicle, and then the machine learning part. So those who are now, so forget about thermal part. So we already discussed CFD, electrochemical, thermal, and all those. But now, if you guys or any professor is working on machine learning, then I can definitely provide the data and we can work in collaboration. Then model validation, couple of papers, and the collaborative work. Again, personal introduction, I don't want to go, but just to let you know that this is my profile, my email ID, and if you scroll down my profile at the end, it is written, I don't see right now because it's a screenshot. At the end of this, at the bottom side, you will see I am supervisor, or I'm accepting the new like the grad student basically. Again, my personal info, educational info, Google Scholar profile. I think, as I said earlier, I have 9,000 citations, working closely with Michael Fowler, professor in chemical department, and then Professor Roydon Fraser, and then my couple of papers. Awards and membership, I already explained. Again, I don't want to go into this part, but I think I did not explain about my membership. So Professional Engineers Ontario, so PEO is very reputed, the agency or company, or the government licensing. So if you want to work in a government sector like Canada Post or Transport Canada or those government sector, we need this license, and I'm a member since 2016 also for this one. So this is very reputed license in Canada. Outstanding Teacher Award, I already explained about engineering. So engineering thermodynamics course. Gaia lab, yeah, I already explained about this lab, and we have this vehicle you can see over here. So in Waterloo, on the back side of Waterloo, we have big, the research area, and we do this type of, like the battery testing or like the autonomous vehicle testing also. By the way, I'm little involved in this in this one, but my another research area, it is not explained over here, but that is the hydrogen fuel cell. So anybody who is working on hydrogen fuel cell, we have funding only for 1 year, and that is for the postdoctoral fellow. So if someone is looking for experimental on the hydrogen fuel cell, we have experimental setup ready. So there was one student, he was Indian student, very good student. His name is Munindra Prasad. So he finished his PhD under me, and then I requested him to continue with the postdoc. But what happened? He got a very good job in Toronto with a startup company of $100,000. So he is no more in the Waterloo. I'm looking for one postdoctoral fellow for that particular project. Ramya, I will come back to you for that part. Again, this is Waterloo Institute of Sustainable Energy, Professor Fraser and Professor Fowler, Chemical and Mechanical Department. Couple of papers on applied energy, electric power research, blah, 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 like that one. Again, Google Scholar part, reviewer, fine, Waterloo, fine. I already gave enough information about Waterloo. So feel free to come to Waterloo. This is about the Waterloo. Probably let me explain. Let me show this one. I did not know about that. Guys, is this audio clear? I don't know. Hold on.
No, it's not.
No. The video.
Video is
No,
okay,
it's
sir.
not.